Good afternoon, everyone. So today we are very happy to have Marina Huerta from Bariloche to give us the seminar on entanglement, global symmetries, and topological contributions. So Marina, please take it away.
Okay, many thanks. Hello, everybody. Many thanks for the invitation. So the talk will revolve around the physics that connects entanglement, global symmetries, and topological contributions. The idea is to discuss what happens to the entanglement entropy when the theory you are considering is based on an algebra of operators that are invariant under a global symmetry. And okay, we will see that in these cases, there are some expected properties, additivity and duality, or duality, that are not satisfied. This is the reason for this is a consequence of the existence of some operators called intertwiners and twists that cannot be locally generated within the region or its complement, respectively. So this structure gives rise to a not uniquely defined entanglement entropy, and is within this scenario that novel contributions can arise. Okay, so now most of the discussion is based on this article here. Okay, entanglement entropy and superselection sectors, global symmetries. This is a work done in collaboration with Horacio Cassini, Javier Magan, and Diego Pontello last year in Bariloche. Okay, so good. No. Okay, here. So I will start with a short review of some preliminary definitions and dedicate some lines to the strategy and perspective we will follow during the talk. So let's start with the entanglement entropy definition. So suppose you have a state in a quantum system, then the entanglement entropy associated to a region is defined as the standard von Neumann entropy associated to this density matrix, which is restricted to the region R by tracing over the degrees of freedom that lives outside your region. Okay, and this is a good measure of entanglement between degrees of freedom inside and outside when the global state you are considering is pure. Okay. Now the point is that when your theory is a quantum field theory, the entanglement entropy is a divergent quantity. So in order to give sense to it, you need to introduce a regularization scheme. Okay, this could be taken as a bad signal, but what is encouraging is that once you have a regularization scheme, the entanglement entropy admits an expansion of this type in powers of the UV cutoff, this epsilon here, with a strong geometrical character, in the sense that these coefficients here in the expansion are local and extensive functions on the boundary. Okay. Now, again, if you look carefully at this expansion, what happens is that in general, all these coefficients will be regularization dependent, except for the C dot that in the case you are considering a conformal theory and a spherical set, can be identified with the trace anomaly for even dimensions and with the free energy in odd dimensions. And what is more interesting is that if you combine this result with the strong subadditivity property of the entanglement entropy, this gives you all the elements you need to prove, for example, irreversibility of the renormalization group flow in 2, 3, and 4 dimensions. Okay, another remarkable point about entanglement entropy in quantum field theories is that this is a quantity with an holographic dual, okay, known as the holographic entanglement entropy. And this is probably inspired by the celebrated area law that of the entanglement entropy, in the sense that the leading divergent term here in this expansion has units of an area, okay? So now, okay, now regarding the strategy we are going to follow, having in mind that the entanglement entropy involves states and regions, and on the other hand that the algebraic approach to a quantum field theory is based on algebras of operators corresponding to causal space-time regions, then it's natural to think that the algebraic approach is probably the better one to use to understand problems concerning entanglement entropy in quantum field theory, okay? Even more if you are thinking on introducing global symmetries, okay, in the description. Basically the strategy will be to focus our attention in the algebra region assignation problem, and this is what I have tried to show you in these schemes. In fact, theories with global symmetries within this perspective can be seen just as subsets of invariant operators. This is a problem that was studied many years ago, and within this formalism, these theories with global symmetries are known as theories with superselection sectors, which means that the global Hilbert space splits in sectors characterized or labeled by the charges, okay? What we will see later is that is exactly in these cases where the assignation of a local algebra to a region is not unique, and this in turn implies that the entanglement entropy is also not unique. Okay, so next, okay, the motivations. Okay, so our motivations to study the problem of entanglement entropy and global symmetries is to try to understand a set of results, all concerning models with symmetries that could not be explained, let's say, by the tools at hand at that moment. So the anomaly mismatch for gauge theories is one example of these puzzling results. So a very short time after the identification of the log coefficient in the entanglement entropy expansion with the anomaly was proven the same year, I believe, by explicit calculation. Docker found a mismatch for the Maxwell theory. So for us, this was a puzzling result for many years. And the reason is that the solutions to the problem proposed along the years are all based on the idea. Here you have some references. So the solutions, I was saying, are all based on the idea that there are boundary degrees of freedom that could give the missing contribution in order to match the anomaly. This is a classical contribution in a sense, but the point is that all these results strongly depends on the regularization. So in order to get rid of this regularization dependence, our first try was to try with mutual information. But okay, what we found is that mutual information cannot solve the problem. And the reason is very shortly as follows. Suppose let's take 2 dimensions in space, for the space 2 dimensions, and you have this region, a square, okay? And suppose you regularize your theory, putting the model in a lattice, and for a gauge theory in general, your operators will be associated to links in the lattice and to the plaquettes, okay? And it's clear that you have an infinite number of choices in the assignation of operators to the region. Here we have 2 examples. In the first one, we decide to keep all the plaquettes and all the links. And in this one, in the last one, we decide to keep the plaquettes, but to erase all the links on the boundary. Okay, these 2 choices correspond to algebras with a center. A center is the set of operators that commutes with all the operators in the algebra. And we know that the centers exactly gives you the same kind of classical contributions people were talking about in the results I mentioned before. But the bad news is that this classical contribution does not survive the continuum limit in the mutual information. So our conclusion was that the inclusion of centers cannot be the final solution, okay, to the anomaly mismatch problem, okay? So this is just to give you a little bit of the historical perspective of the problem we are dealing with, okay? So next, this is the plan of the talk. First, I see, yes?
I'm sorry for the interruption, ma'am. I just wanted to know what is causing the anomaly mismatch.
Could you repeat your question?
Yeah. What is causing the anomaly mismatch in gauge theories?
The anomaly mismatch means that, what I mean with the anomaly mismatch is that we know that the log coefficient, perhaps we can go to the first slide. Okay, the log coefficient in 4 dimensions, in particular in 4 dimensions, is proportional to the trace anomaly, okay? And what Docker did was an explicit calculation of this coefficient, okay? But instead of finding the trace anomaly, he found a different number here, okay? So for the Maxwell model, he did the same calculation for scalars and for fermions, and the match was perfect. But for the Maxwell field, there was a mismatch, okay? This is what I mean with the anomaly mismatch. Sorry Perhaps it was not clear.
Is it, I'm sorry, ma'am, is it assuming some kind of holographic duality? Okay, I'm sorry, I don't know much. I don't know anything about anomaly mismatch. I'm very sorry for the interruption, ma'am. But I just wanted to get some intuition as to, I know about conformal anomalies, but what anomalies are we talking of here?
This is the trace anomaly, okay? In 2 dimensions, for example, is the Virasoro central charge of the conformal theory, okay? So, in fact, we are not going to talk about this problem particularly. This is just a motivation why we were interested in studying entanglement entropy for theories with symmetries. And this is in particular one problem that appeared just after proving this identification I'm talking about, that was in a way puzzling and ask for a deeper understanding, okay, of what happens when the quantum field theory you are dealing is, you are considering has local or global symmetries, okay? So I was in the plan of the talk, so I was saying that I will start commenting on some properties we expect the algebras satisfy when in the assignation of algebras and regions in quantum field theories. Then we will introduce global symmetries, okay, in the discussion, and to connect with entanglement entropy, we will have to discuss a little bit about relative entropy and introduce conditional expectations. Okay, this will give us the connection of the structure and the general structure to the entanglement entropy. And finally, we will see how for regions with non-trivial topologies, novel universal terms in the entanglement entropy arise. And if we have time, I would like to illustrate all this structure in a particular example, the chiral scalar in 2 dimensions, okay? Following the algebraic approach, the first step to clarify the problem we are dealing with is to revise the properties these algebras should satisfy. And okay, yes, as you will see, all of them are easy to guess. So the first one is called Isotony. And what tells us is simply that if you have an operator that belongs to the algebra of the green region, this operator also belongs to the algebra of the blue region, taking into account that the green region is included in the blue one, okay? So next, this is we call additivity property, and what says is that the algebra of the union of these two balls is given by the union of the algebras of the green and the blue region. What is behind this is the notion that the operator algebra of a region can be generated by the algebras of operators of smaller regions included in the region. So this is again a very natural property. And okay, now we know because of causality that local operators at the spatial distance commute. Here with R prime, I'm noting this corresponds to the complementary region of R, okay, containing all the points that are spatially separated from the points in the region. And this directly implies that the algebra associated to the region has to be included in the commutant of the algebra of the complementary region. Okay, the commutant is the set of operators that commutes with the algebra. But now what you can ask yourself is when this causality property can be improved in order to give you an equal here. This is known as Haack duality, and okay, for simply connected regions and most quantum field theories, in fact, this Haack duality is satisfied. What it tells us is that the algebra of the region is equal to the commutant of the algebra of the complementary region, okay? But what is not so direct is to think what happens about regions with non-trivial topology. So, for example, we can consider a region which is the green region, which is the union of these two balls. The blue region is the complementary region. So for sure, we know from causality that the algebra of the green region is included in the commutant, okay, of the algebra of the complementary region, but it's not clear if for all quantum field theories, this inclusion of algebras can be improved to give you an equality, okay? So let's keep this possibility in mind, and let's see what happens if duality is not satisfied for a certain region. Okay, so in general, suppose we are in this situation that duality is not satisfied, so you can think that it's always possible to add some operators. I call it here A, in order to restore the duality property, okay? And we will call this enlargement of the algebra the maximal algebra associated to the region. Of course, the price you have to pay is that this algebra A has the additivity property, but you lose this property once you introduce these new operators, okay? So you gain in duality and you lose in additivity. But what is interesting is that the breaking of duality in a region forces a dual breaking in the complementary region, okay? But again, you can do the same. You can add new operators, B, in order to restore duality, but of course you break additivity in this maximal algebra, okay? And what is clear, or also easy to see, that these extra operators do not commute with each other, okay? In these cases, to construct nets, these are assignations of algebras to regions, satisfying duality requires introducing some extra operators. This will be the twist and the intertwiners, we will see later. And these generalized sectors, we can call it generalized sectors, the classes associated to these extra operators arise by a quotient of the maximal algebra with respect to the local algebras, okay? It's also possible to prove that these classes define a natural notion of fusion, but we are not going to use this part during the talk, okay? This is just a comment. So now let's see that this is exactly what happens when the theory, when your model has a global symmetry, okay? This breaking of duality and this possibility of restoring the duality property at expenses of breaking the additivity. And okay, let's see how this works in a simple example. Our model is the free Dirac field restricted to the algebra of bosonic operators. This is the O model, okay, I call it O. And the operators living in O only contains an even number, okay, of fermionic operators. All these operators are invariant under the set 2 symmetry. And okay, now we can, in the model F, in the complete model, we can consider the following localized operator, which is a charge operator, okay? Here alpha is a smearing function with support within the region. And clearly by construction, this operator does not belong to our model. But if you have two regions, we can construct something, an operator called Intertwiner, which has one leg, I mean, just combining two of these, with one leg in one region and one leg in the region 2. So this operator belongs to the global algebra. Okay, this is a scheme of that. So suppose our region is the union of these two balls. The intertwiner looks something like this. You have a charge operator in this region and a charge operator in the other region. So the intertwiner belongs by construction to the commutant of the complementary region, which means that commutes with all the operators in the blue zone, okay, in the blue region. But does the intertwiner belong to the algebra of the union? Okay, it's the answer is very, very easy, because the additive algebra, okay, is the product of even operators in the right and in the left. So clearly, the intertwiner does not belong to the local algebra. So this intertwiner operator, we have identified the intertwiner, and it's easy to make the identification with these general operators A needed to restore, okay, the duality property, okay? Now, what happens if you pay attention to the complementary region? Okay, for the complementary region, the commutant, what is easy to see, is that the commutant of the algebra associated to the green region, so the operators that commutes with the operators in the green region, contains an operator called twist that has this form here. Is just the exponential of the integral of the charge. So it's the operator that implement the symmetry transformations locally. Again, we have a smearing function here, which is 0, okay, in the region 2, and 1 in the region 1, and in the middle goes from 0 to 1, okay? So it's easy to see by construction that the twist belong to the commutant, but do not belong to the algebra of the blue zone. So this is belongs to the family of these B operators that we need in order to restore duality. Okay, and again, since we have the explicit expression for these two operators, we can check that effectively do not commute with each other. Okay, so our conclusion is that this structure is exactly what happens in general for any global symmetry. So this is a summary of the algebraic structure in models with global symmetries. So you will have the additive algebras that can be completed with some extra operators, the twist and the intertwiners. Okay, the twist will be labeled by an element of the group, and the intertwiners will have the representation index. Okay, so this gives you the maximal algebra that includes obviously the local algebra. This maximal algebra does not satisfy additivity. Okay, so this is the general structure we have for theories with global symmetries. Yes.
Can you clarify what you mean by global symmetries here?
By global symmetry?
Yeah.
Well, it's your model only contains operators that are invariant under a global symmetry in this case. So in the example, in the simple example I showed you before, the global symmetry is a set 2, for example. All the operators living in your model, so you are interested in this model O, and all the operators that belong to your model are invariant under this symmetry. Okay, so of course this can be a similar structure appear when your symmetry is local, but still let's keep the discussion for global symmetries and okay. Is it more clear? Okay, so
symmetry, the meaning, I don't seem to be understanding that the setup which you have organized, the global symmetry can be anything, no? Not necessarily only the Z2 symmetry which you were referring to. Do we have a good intuition as to what it is in the general context?
Well, in the algebra context, it's very easy to say, because it's just to restrict your algebra. You kill from the full theory, you kill all the operators that are not invariant under your symmetry. So from the algebraic perspective, is very short, the description. So it's just a subset of invariant operators that you assign to your region, okay? And it's in this assignation of invariant local operators that these problems arise, okay? So you break duality, or you break additivity. If you want to restore duality, you break additivity, but it's only when the set of operators you are considering is a subset of the full theory, okay?
And do we ensure that twist and intertwiners restore the Hague duality always?
Well, the point is that you have to choose. I mean, you have two choices, and in fact, in a way, if you want, this is not an ambiguity, but corresponds to two models from the entanglement entropy perspective. I will show you that, in fact, if you choose to keep the model based on the local algebra, you have one entanglement entropy, but if you instead you choose to base your model on the maximal algebra that satisfies duality, you have a different entanglement entropy. I will go to that later, okay?
Thank you.
This is from the entanglement entropy perspective, okay?
Yeah.
So, so now we are going to that point now. So to make contact with entanglement entropy, it's useful to introduce the notion of conditional expectation. So given an inclusion of algebras, this is the kind of situation we are dealing with. Conditional expectation is a linear map from the bigger algebra to the smaller one that satisfies this property here. This is something we are familiar with, perhaps not with this name, but for example, tracing out a factor is a conditional expectation, okay? Suppose you have this situation, the tracing over the degrees of freedom lying in the algebra A is satisfies this property here and is a conditional expectation. Okay. Another example is our case is the quotient by a symmetry group. Okay. So in the conditional expectation, you take an operator in the algebra, in the full algebra, and it gives you an operator in the restricted algebra. Okay. So what is interesting is that conditional expectations can be composed with states, in the sense that if you have an state living in the restricted model, you can compose this state with a conditional expectation. This takes an operator of the full algebra and gives you a number for this state in the restricted model. Okay, sorry. So now let us remind the definition of the relative entropy. Okay, this is going to be useful to to consider entanglement entropy in all this structure. Okay, the relative entropy, this is the definition. Relative entropy involves two states, and in a way is a measure of the distinguishability of the states, and it can be used to define mutual information. Okay, this is the relation. This is, I mean, the mutual information between two regions, A and B, can be written in terms of a relative entropy in this way. Perhaps you are more familiar with this definition for the mutual information in terms of entanglement entropy. And now we can combine these two concepts, relative entropy plus conditional expectations, and in this way you can find a relation between relative entropies in the restricted and in the full model. Okay, this will be a very useful relation for us, and in particular what we are going to use is the case for any two invariant states, invariant under the conditional expectation. So what tells us this relation is, in a way, that the distinguishability between these two states cannot be, if the states are invariant, cannot be improved by enlarging the algebra. This is a very interesting property. So,
Excuse me. Question?
yes, please.
Can you just remind me what the conditional expectation is, and how do I physically understand what it is?
Yes, here, the conditional expectation is just a map. So suppose it's just a map from the full theory to the restricted theory. So the conditional expectation acting on operators, okay, leaves invariant the operators in the restricted model, and gives you acts only on the operators of the full theory. Okay.
Okay.
So
no, I mean, what kind of map? I mean,
perhaps what is interesting is, for example, if you want to calculate the expectation value of an operator that lives in the full theory, doing this composition, this object here does the work. Okay, you take an operator of the full theory, and thanks to the conditional expectation, this gives you an operator in the restricted model, and then you can calculate, for example, the expectation value of this operator. Okay.
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 Okay. Thanks.
Ma'am, can we? I just had a very small confusion, ma'am, if you don't mind, in the definition of the conditional expectation. So, can you go to the definition of condition? Yeah. In this case, the expectation value of operators B1, A, B2 is same as B1 times the expectation value of A into B2. B1 and B2 here are operators, no? Elements of some algebra O. Ma'am, am I audible?
I don't know if I understood well your question, but basically the expectation value kills all the part that is not invariant. Okay, so if you have a combination of operators and you apply the expectation value to this quantity here, what the conditional expectation will do is to pick only the invariant part, okay, of this operator. So for example, this is our case, okay, a quotient by a symmetry group. So the conditional expectation will only pick up the operators that are invariant under the symmetry, so gives you an operator that lives in your model. Okay, perhaps with the examples later.
I'm just confused with B1 and B2 are operators, no? So how do we have...
Can you save your questions for later? I mean, give the speaker a chance to.
Yeah, I'm sorry.
Okay. So we were here. So now how to connect all this general structure to the entanglement entropy of a region. So as I already said, the entanglement entropy does not properly exist in quantum field theory. It's just an infinite quantity. But what we can do is to consider instead a definition to define the entanglement entropy as a regularized entanglement entropy in terms of mutual information. So the entanglement entropy of the region R can be thought as half of the mutual information between region 1 and 2 in the limit that this blue region is very thin, okay? But of course, this way to define entanglement entropy introduces a non-trivial topological configuration. So if our model has a global symmetry, we know we are going to have, we are going to be in the presence of this structure I already described. So we know that if our model has global symmetries, we are going to have two choices for the algebra of the green zone. Okay, the one which is additive and the one with an extra operator, the intertwiner, okay? This satisfies duality, and this, on the other hand, this satisfies additivity. And of course, given these two choices, we have two relative entropies, okay? Based on these two choices. So we have two mutual informations. Of course, these two algebras are related by a conditional expectation that takes operators in the enlarged algebra and gives you an operator in the additive algebra. So the previous formula involving relative entropy and conditional expectations gives you that implies that the difference of these mutual informations are just a relative entropy, okay? If you are considering invariant states. So this is probably the more important result. And okay, then a different problem is if you can calculate explicitly this quantity for a particular case, okay, for a particular model. But okay, since we have only a few minutes, 5 minutes, so I have still 10 minutes or something like this?
Yeah, sure. We have
Okay.
some questions in between, so go ahead.
Okay, so perhaps we can skip here. The discussion here is about bounds. You can find upper and lower bounds. You can find for this relative entropy using monotonicity of relative entropy, this property of the relative entropy. It's easy to bound this quantity, but we can skip this part and just go to, okay, here to the list of explicit results, okay? So how to find these novel universal contributions to the entanglement entropy. So what you have to do is to calculate explicitly this relative entropy, okay? And in the case we are interested in, which is the one of complementary regions, this is the situation that is connected or related to the entanglement entropy through mutual information. The answer is that, for example, for the case of finite groups, you have a constant extra contribution given by this log G. For Lie groups, the case of Lie groups, you have a logarithmic contribution, and for the case of, okay, these results are valid for any dimension, but in particular for D equal 2, this log contribution becomes a log-log contribution, okay? So if, for example, if we think in the anomaly mismatch problem, we see here that this kind of structure admits a new logarithmic contribution that, in the case that your symmetry is local for the or you have a gauge symmetry, could give you an extra contribution in order to match the anomaly. But this is just a comment. It was not what I was discussing here because we were dealing with global symmetries, but just to connect with what I said during the motivations, okay? The same thing can be done for, all these results are for the case of two balls, okay? But the same thing can be computed for the case of multi-component regions. And what appear here is the number of boundaries of the region. So that's why we said that in a sense, these are topological contributions. And also you can compute the relative entropy for the case of spontaneous symmetry breaking scenarios. Obviously, in this case, you have one more parameter, which is the spontaneous symmetry breaking parameter. So you have two possibilities depending on the regime you are. But okay, if you agree, I would like to dedicate the last 5 minutes. We have to illustrate all these general results in a particular example where all the computations can be done exactly. Do you think I have enough time to discuss this? It's not very long.
Yeah, I think you still have 5 to 8 minutes.
Okay, it's going to be enough, I believe. Okay, so the model I would like to discuss with you is the chiral free scalar in 2 dimensions. This is a conformal model, okay, with a central charge 1/2, since we are taking out only the chiral part. And the algebra is this corresponds to the algebra of the current. The algebra is generated by the derivatives of the scalar, okay. And what is interesting in this model is that all the operators of our subalgebra are operators of the fermion algebra that are invariant under charge transformations, okay? So this is an example of a U1 symmetry, okay? An orbifold, the orbifold that results from a quotient by this symmetry group, okay? So in this model, we know the Hamiltonian, we know the commutation relations between the current, and since this is a Gaussian model, we can compute exactly the entanglement entropy, mutual information, so we can check duality and additivity properties. For example, if we put our model in a lattice, or also analytically, okay? But for example, suppose you choose to check duality using entanglement entropy, and you put your model, in order to have a bounded region, you put your model in a circle, and you have 4 intervals in the circle. In order to check duality, for example, for one interval, duality would says that the entanglement entropy associated to the interval 1 is equal to the entanglement entropy associated to the union of all the 3 intervals. And for the case of 2 intervals, duality would imply that the entanglement entropy of the red region is equal to the entanglement entropy of the green region, okay? So this we know how to do this calculation in the lattice for Gaussian models. And okay, I will show you the results later. But of course, other possibility is try to check duality, but using mutual information, okay? In order to get rid of, if you don't trust entanglement entropy because it's regularization scheme dependent, you can use instead mutual information. And in order to check duality, at the end of the day, what you find is that Hug duality means that this function u has to be symmetric. So let me show you what is this function. So for that, let's consider the mutual information between the intervals, the red intervals, and also the mutual information between the green intervals, okay? So if we assume duality, the entanglement entropy of the union has to be equal, okay? And so we can combine these two mutual informations in order to have this expression here. Here, eta is the cross ratio, okay, of the 4 points in the line, and we know that in general, for any conformal field theory in 2 dimensions, in 1 + 1 dimensions, has this form, okay, has a logarithmic term proportional to the central charge plus a function u that will depend on the theory you are considering, okay? For example, for the fermion, this u function is exactly 0, and what we should check is that for this model for the chiral free scalar, this u function is symmetric. If this u function is symmetric, okay, this is equivalent to say that the entanglement entropy of these two unions is the same, so you have Hug duality, okay? So now the results, this is what I obtain in the lattice for one interval. This is the entanglement entropy in terms of the size of the interval, and as you can see, this gives you a symmetric function. So for this case, a trivial, if you want a trivial region with a trivial topology, you have Hug duality, okay? But now if instead we take a region with a non-trivial topology, the union of these two intervals here, I choose to put two intervals with the same size, okay? And what is in this, in the figure, what I have done is to move the size of the intervals and calculate the entanglement entropy, okay? If we have Hug duality, of course, this function should be symmetric, and it's clearly the result is that clearly we don't have Hug duality for this configuration, okay? Now for mutual information, this is what we get for the function u for the chiral scalar. It has this complicated expression in terms of an integral of hypergeometric functions, but still you can solve this integral numerically, and this is what you get. So clearly this is not symmetric, okay? And also what is more surprising is that, in fact, you can check that in the regime of a cross ratio very close to 1, you have this log-log contribution, this universal contribution we were talking about before. So, okay, just to finish, where are the twists and the intertwiners in this model? Okay, the twists and intertwiners are very easy to construct. For example, if you take the difference of the scalar field in 2 points, one in the first interval and one in the third interval, what you get is just an operator that belongs to the global algebra, but does not belong to the union, okay, and belongs to the commutant of the complementary region. So this is a kind of intertwiner, if you want. The same thing can be done with an operator with a leg in the interval 2 and in the interval 4. This would be the twist. And this is a summary of the algebraic structure of the model, okay? These two operators do not commute. And again, we can enlarge the additive algebra by adding this operator with one leg in the interval 2 and in the second leg in the interval 4, and the same can be done in the complementary region in order to get something which is we have called the maximal algebra, which has this expression here. So okay. Conclusions. Okay, theories based on subsets of local operators. This is what we have seen. Invariant under some global symmetry lead to a hack duality or additivity violation. The reason is the existence of twists and intertwiners. In this case, we have seen that the assignation of algebra to a region is not unique, and this in turn gives rise to a novel topological contributions, okay, to entanglement entropy. Just a comment, to make contact with the motivations, the anomaly mismatch mentioned during the motivations. Okay, local symmetries give rise to the same structure. I believe that Horacio told you about local symmetries, I don't know, a month ago or something like that. So this violation of additivity duality also appears for the case of local symmetries. You also have these non-locally generated operators. In the case of local symmetries, are called Wilson and Toff loops. Okay, so this give us the solution to the mismatch of the Maxwell anomaly. Okay, so thank you.
Thanks for the nice talk. Maybe we can still take 1 or 2 more questions, since we have already some questions during the talk.
Hi, it's Luca, Marina.
Hi, how are you?
Very well. I had a question. So just to try to understand this log G, you said in the discrete case, right?
Yes, it's a constant term in the entanglement entropy.
Yes, but I was trying to. So is it?
It would be a log 2 in the case of set 2. Okay.
Yes, but is it model dependent or is it generic?
No, it depends. It depends on the symmetry group.
So if I take whatever model with Z2, there will be
You
always these.
you will get a log 2 depending on the choice of your local algebra.
Mhm.
Yes.
Okay, because the intuition is that my reduced density matrix will be block diagonal, right? I will have an even sector and an odd sector, and so in order to get this log 2, how do I understand it in this setting? Because I understand that the operator that I'm not considering if I don't put the intertwiner would be the one that changed sector, right? So
yes.
And then is there an easy way to see this log 2?
No, perhaps, Luca, perhaps what is more transparent is that this is in the entanglement entropy. In fact, I'm working on something like this. It's this contribution is unstable, okay, because depends on the details of the theory, how you put the theory on the lattice, for example, or even how you define the full theory. But what is more transparent is that this quantity is well defined. Okay, this is the mutual information for the full theory. Okay, the mutual information between two regions, complementary regions in the full theory, and then you compute the mutual information in the restricted model. But mutual information in the restricted model means that you are taking the additive algebra of the restricted model, okay? Because this is the only well-defined mutual information. Mutual information means you take the entanglement entropy of a region, the entanglement entropy of the second region, and then the union of the two, okay? You cannot mix languages. Yes. So this is a well-defined quantity. In terms of entanglement entropy, you are right that it can be subtle to get this log 2 if you want a set 2 case. It could be subtle. Yes, I agree with that.
I see. Okay, thanks.
Anyone else has a question?
I have a question. Marina, thanks for the great talk first.
Thank you.
Second,
Ignacio.
when you, so you explained that, my question is about this term of a maximal algebra, I think you called it.
Yes.
So you said that if we include these other operators, say the intertwiners in one case or the twist in the other case, you get a maximal algebra, but what does that mean?
Okay. It's a good question, yes.
Or like, is there an obvious way to see that there are no other operators?
No, my explanation was not clear enough in the sense that the max, due to, I call it maximal because due to causality, you need, okay, the algebra associated to the region has to be included in the commutant, okay? So the best you can do is to have duality, okay? This is the best you can have because of causality. So if you find a set of operators that to complete your additive algebra in order to have duality, this is the best you can do. That's why I call it this one the maximal algebra, okay? Because it saturates the causality property. And I call it this one additive algebra because it satisfies this this property here, okay? Sorry, I was not clear enough.
Yeah, okay, thanks.
Thanks.
I have a question, if there is time.
Sure, maybe the last question.
Hi, Marina. Can you just remind us what remind me what the intertwiner and twist are exactly and what they're supposed to do?
Yeah, of course. Suppose you find your algebra does not satisfy duality, okay? So you calculate, I mean, your additive algebra, it's clear how to be defined, okay? You take the algebra of one ball, you take the algebra of the other ball, and then you take all the operators together, okay? And you have the additive algebra. And on the other hand, what you can do is to take the algebra of the complementary region, okay? And then to calculate the commutant. So the sets of operators that commute with all the algebra of the complementary region.
Okay.
If you have Haack duality, these two things should be the same. But suppose it happens that it's not the same, so there are some missing operators you need to add in order to complete your algebra and restore duality, okay? These operators you need to complete the additive algebra in order to restore duality are the intertwiners, if you pay attention to the region R, or the twist if you pay attention to the complementary region. This is just the name, or Wilson loops or Toff loops in the case of local algebras, okay? But if you ask me, what are the intertwiners and twists? Okay, to construct the intertwiners and twists could be very difficult depending on the model you are considering. Of course, I have chosen two simple examples where it's very easy to find the explicit form that these twists and intertwiners have, okay? But I agree with you that in general, for any model, it's not going to be easy to find the explicit form these intertwiners and twists have, okay? So this is just the general structure, but I'm not saying that we are able to calculate twists and intertwiners in any situation, okay? Is more clear or?
Well, just a quick follow-up. So if R prime is the complement of R, right, then R is the complement of R prime, right?
Yes.
So wouldn't the notion of twists and intertwiners switch in that case? Wouldn't the intertwiner, if you take R as the first region and R prime as
of course, it's just, yes.
Right. So
in a sense, these two relations here are, for example, in the 1+1 example I show you in the case of the chiral scalar, intertwiners and twists are the same operators, okay?
Okay.
So these are perspective dual, one from each other, yes.
So when are they not the same?
Well, in the case I show you, in this case, are not the same.
Okay. All right.
The intertwiner has one leg here and one leg here, and the twist operator is just the integral of the charge from the boundary. The twist operator associated to the region 1 is the integral of the charge, the exponential of the charge from the boundary along all this region here, okay? So in this case, in this example, are different. Okay.
Okay. Thank you.
Thank you.
Yeah, let's thank Marina again. Thanks for your very nice talk.
Okay, thank you.
if you, I don't know if, so I will stop the recording now.